lowest score. Okay. Anyway, so unless you miss multiple quiz, you shouldn't have problem. Like the quiz shouldn't affect your grade. But if you miss multiple quiz, that's your business. Okay. I mean, you cannot explain like you miss multiple quizzes like because of sickness. If you are so sick that you have to miss multiple quizzes, well, I can only suggest that you probably want to, drop this class. Okay. 就是我们这 quiz 哦，这个我们不给这个补考的哦。就是如果说你们有人讲说，我那个这个因为生病哦，我会 miss 掉这个 quiz， 那没有问题，没有问题。反正我们的 quiz 本来就是取最高的几个成绩哦，所以说你如果说 miss 掉一次，什么跟生病的关系，其实是没有关系的，这个完全不会影响到你的成绩哦。你会影响到成绩，除非你会错过好几次的 quiz。那如果是这样子，你说全部都是因为生病，而不是因为你自己说 miss 掉，那我只能跟你讲说，你可能这一堂课你就要 drop 掉，因为你身体有状况这样。OK， anyway， so just a reminder, okay, just a reminder. And we have, how many lectures do we still have before the final exam? 还有4次吧，是不是？还是连今天这一次4次？
我看一下。
I forgot. But the final exam is like in the final exam week, okay? So that's like, you guys know about that, like I think that's like the Wednesday prior to the Christmas. It's the Wednesday prior to the Christmas. That's your final exam, okay? So yeah, just want to remind you, okay? And we still, including today's quiz, we still have like 3 quizzes. And 这次今天这是第4次，对不对？所以后面还有2次，然后还是期末考 ，OK？ So we still have a lot of points for you to earn, okay? So if you do not perform good enough, okay, at the beginning of the class, okay, don't give up, okay. That's like you still have like a chance to make up, okay. So anyway, so come back to this to what we covered like last. I think we start like on this slide, okay. But I only had a chance to mention about this theorem, but I didn't have time to prove that. But basically, okay, Rn is like S, okay, direct sum, okay, S, I don't know how to call that. Okay. Anyway, so that's like basically, okay. How do we prove that? Okay. Assume, okay, we have an orthogonal basis of S. Okay. Then with that V1 should be this one. And the V should be V minus V1. Okay. So where V is any vector in Rn. Okay, V is any vector in Rn. Okay, and this V1. If you look at this V1, obviously it's a linear combination of this K vectors. So obviously, this V1 fall into S1, right? Oh, sorry, fall into S. This V1 fall into S. It's an element in the subspace S. Okay, and then I mean, because of the setting, we know V equal to V1 cross V2. That's a key. And then we understand that you can try to check. You will find that V1 is the inner product of V1 to W1 is 0. Okay, why? Okay, so you try to do like the inner product. Okay, you will find that because like all the other bases are the inner product of W1 and W. For example, W1, W2, or W1, W3, and so on. They are all zeros. So you W1 inner product V1. Okay, the only term left will be this one. Okay, will be this one. So sorry. We need to check. Okay, V2. We need to check V2, not V1, because we already know V1 is in S. We will check V2 is V minus V1. So V2 equal to V minus V1, right? So you can easily check, for example, W1 dot V2 is equal to W1 dot V minus W1 dot V1, right? So this we keep this W1 dot V, okay. But how about this part? This part, as I told you, W1. This is like V W1. So it's something like that, right? So we keep W1 dot V minus. Okay, we know this W1 with W1 dot W2, W1 dot W3. I mean, all these become 0. Okay, so the only term left will be the first term. So it's going to be so what happens is that these two cancel out each other. So this is V dot W1, this is W1 dot V, so this is 0. Okay, so this is the case for V1. Okay, this will be the case for V2. You will find that this is the case for every BI. Okay, so what does that mean? It means that B2 is, is basically perpendicular or like orthogonal to every BI. Okay, sorry, every WI. B2 is orthogonal to every WI. So having said that, B2 belongs to S orthogonal. Okay. So, okay, because we can write any vector B in Rn as like a B1 plus B2, where B1 belongs to S, B2 belongs to S orthogonal. So, well, that basically satisfies the definition that Rn is a direct sum of S and S orthogonal. Okay, based on our previous definition. Okay. So the second one, dimension S cross dimension S orthogonal equal to, and this is like we already proved this earlier. Okay, so not much to talk about. Okay, this is a given. The third one, okay, you can prove, okay, this same set of bases for S is also the basis for like S orthogonal. Okay, that's one way to do that. Okay, another way you can do it is, okay, basically okay, because we want to show right, and the S and the S orthogonal obviously are two sets, right? Two sets. Okay, I mean, of course they are also like subspace of in Rn. Okay, but nevertheless they are two sets. So basically, what you need to do is to show that, okay, can you show this one and this one? I think that if you still remember something from your discrete math tell you about how to prove two sets are equal, right? Right? Okay. So how do you do it? First, okay, if you have a V, if you have a V in any vector in S, we know that, okay, this vector will be perpendicular to any vector in S orthogonal, right? So we know like V dot for any W in S orthogonal, okay, V dot W is going to be 0, right? Right? Okay, based on like the definition of S orthogonal, right? But this also implies that V is an element of S orthogonal, right? have the first one. We have the first one. We have the first one. The first one is a given. Okay. I mean that direction is the other direction. The other direction is we need to show if B belongs to S orthogonal. Eventually, we need to show B in S. I mean, that's our goal. Okay, that's our goal. So first, we know that, okay, we know that regardless, S orthogonal is a subset of Rn, right? S orthogonal is a subset of Rn, right? So if S is in this set, obviously, if B is in this set, okay, let me put it. So if B is in S orthogonal, we can derive B must be in Rn. Any question about that? Because S orthogonal is a subset of Rn, right? S orthogonal actually is a subspace of Rn, but don't worry about that. I mean, we only need to use the property that subspace is obviously also a subset, okay, of that